Question 1. When observing a distant stellar nebula, we observe that the nebula has a strong glow at the frequency f equals 1.5 GHz. If we assume that this glow is the result of cyclotron motion of electrons, what is the strength of the magnetic field in this distant nebula? Please pause the video and attempt this problem yourself. Given that we are looking at cyclotron motion, and given that we have a frequency, it is most likely that we will be using this formula right here. Cyclotron frequency is equal to QB over 2 pi m. If we take that formula and solve for magnetic field, we get that the magnetic field is equal to 2 pi times the particle mass times the cyclotron frequency divided by the particle charge. Since the particle we are dealing with is an electron, the mass is 9.11 times 10 to the negative 31st kilograms, and the charge is the elementary charge of 1.6 times 10 to the negative 19th coulombs. Note that I am not including the negative. That is because the negative will affect which direction the electron spins, not the rate at which it spins. If we plug these values into our formula, 2 times pi times m times f divided by q, we get a total magnetic field of 0.054 Tesla. Question 2. The particle in the image is either a proton or an electron, and it spins 135 nanoseconds in the magnetic field region. What is the strength of the magnetic field? Please pause the video and attempt this problem yourself. The first thing we need to answer is what kind of particle is it? Is it a proton or is it an electron? To determine this, let's use the right-hand rule. So what we know about the particle's motion is that when it enters the magnetic field region, it is moving downward. And then once it enters the magnetic field region, it starts curving to the left. Also, the magnetic field is pointed out of the plane. So if we hold our hand so that our thumb is in the direction of motion, downward, and our fingers are pointed in the direction of magnetic field toward us, and please note that this is going to be a little awkward to hold your hand this way, we can see that the force should be to the left. Since the particle is accelerating to the left, that means that this particle is positively charged. And being positively charged, it is a proton. Given that it is a proton, we can use this formula right here to answer. First, the period. This formula gives the period of a particle moving in a magnetic field. It's given as 2 pi m over qb. One thing to watch out for, the period is the time of a full circle, whereas this particle only spins a half a circle inside the magnetic field region. So if it spins 135 nanoseconds in the magnetic field region, the period is twice that, or 270 nanoseconds. Next, if we take this formula, T is equal to 2 pi m over qb, and solve for B, we get that magnetic field is equal to 2 pi times particle mass divided by particle charge times cyclotron period. We are dealing with a proton, so the particle mass is 1.67 times 10 to the negative 27th kilograms, and the particle charge is the elementary charge of 1.6 times 10 to the negative 19th coulombs. Plug these numbers in, and we get a magnetic field strength of 0.243 Tesla. Question 3. A cyclotron is a type of particle accelerator often used in hospitals for nuclear medicine. A particular cyclotron is composed of two circular plates with a 1.2 meter diameter. In between them is a 15 Tesla magnetic field. What is the maximum kinetic energy of a proton contained in this cyclotron? Please pause the video and attempt this problem yourself. So recall from last semester that the formula for kinetic energy is EK equals 1/2 mv squared. We can use the formula R equals mv divided by qb to solve for the velocity of a particle in that field, v equals qbr divided by m. If r is the maximum radius that the proton can contain, i.e. the radius of the cyclotron, then v is the maximum speed the proton can have. So therefore, using that maximum speed will give us the maximum kinetic energy. If we do plug this speed into the kinetic energy formula, the result is EK equals 1/2 m times v, which is qbr over m squared. Doing a bit of algebra, we get that kinetic energy is equal to q squared, b squared, r squared, divided by 2m. We know the charge of the particle. It is a proton, so it has the elementary charge of 1.6 times 10 to the negative 19th coulombs. The magnetic field was given at 15 Tesla. For the radius, we need to be careful. The information given was a 1.2 meter diameter. The radius is half the diameter, so the radius is 0.6 meters. And the particle mass, we are dealing with a proton, and the mass of a proton is 1.67 times 10 to the negative 27th kilograms. Plugging all of this information in, we get that the total kinetic energy of a proton inside the cyclotron is 6.2 times 10 to the negative 10th joules. As a side note, when dealing with the energy of particles, we often use the unit electron volt. An electron volt is the amount of energy it takes to move an electron across a 1 volt potential difference. In MKS units, 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. To convert this energy into electron volts, we take the energy in joules, 6.2 times 10 to the negative 10th joules, and multiply by 1. In this case, 1 is 1 electron volt divided by 1.6 times 10 to the negative 19th joules. The joules cancel, we're left with electron volts on top, and we have a value of 3.9 times 10 to the 9th electron volts, or 3.9 giga electron volts.